Great. Great. Thank you very much, Susan, for that introduction. Good afternoon, everybody. Thank you all for being here. My name is Nandini Dendukuri, for those of you who don't know me. And I'm an associate professor at the Department of Medicine. I'm located at Core usually when I'm not working from home. And I'm the person who's organizing the biostatistics seminar series at Core. So we actually have a very interesting lineup of talks for this 2021-22 year. So based on feedback from people at Core, we've got a talk on DAGs and on latent profile models, on propensity scores, and others that are coming up. But this first talk is going to be on diagnostic test accuracy meta-analysis. And I'm very pleased to introduce to you, for those of you who don't know, Ian Schiller, who's a biostatistician at the Core, who has been working in collaboration with me for over a decade now. And so Ian and I have been co-conspirators on a number of diagnostic test accuracy meta-analyses, and I thought that that would be a good topic to share with all of you today. So I'm just going to share my screen. Okay, go. Okay, and no, I'm not sure why I'm not at the top. Okay, there we are. All right. In fact, I'd just like to say a couple of words. Ian is trained at the University of Quebec à Montréal in Bayesian statistics before he joined Division of ClinEpi and now the Core. And as for myself, I've been involved in a number of latent class analysis. That has tended to be the interest of my research program. But because of my involvement with the technology assessment unit, I ended up doing a lot of meta-analyses and strangely diagnostic test accuracy meta-analyses. So Ian and I have written a lot of programs over the years to make these methods accessible to people across the globe. And for some reason, our collaborations have tended to be in the area of tuberculosis diagnostic tests. We've done a lot of work, perhaps because of our acquaintance with Madhukar Pai, who in turn introduced us to Karen Steingart, who's active with the Cochrane collaboration. We did a lot of diagnostic test meta-analyses in that area. But both of us have an interest in Bayesian methods. So that was our preferred method of inference. And for today's talk, nonetheless, I decided to change the motivating example and talk about something we worked on more recently, which is coming from the COVID-19 diagnostic test accuracy literature. So the talk will be outlined as follows. First, I'm going to present our motivating example, and then I'm going to give you a brief outline of what diagnostic test accuracy meta-analysis involves. We'll consider both the situations where the reference test can be assumed to be perfect, as well as the situation where it's not perfect and you want to adjust for the accuracy of the reference test. And finally, I'll hand it over to Ian, who will present an R-Shiny app, which we've developed during the last year to make these methods that we've developed more accessible to a wider audience. And while we were preparing this session, Kabiri actually had suggested that we could have more ask the professor type formats for our seminar series. I think basically make the methods presented more suitable for learning, exercise. And it so happens that the material that we'll cover today is material we usually cover in a workshop setting, Ian and myself. And we'd be glad to offer a workshop at CORE. If there's any interest in a workshop, you can leave a message in the chat or you can send me an email. And I think we'd be glad to offer a workshop perhaps early in the winter. So I'm going to get started. For the motivating example, I decided to pick, like I said, something we'd worked on more recently. And the picture there of that man grimacing while being tested for COVID-19 infection is something now we've all seen over and over again in the last year. And I just see a query in the chat. Just okay, that's Teresa who wants to take our workshop. Great. But so I think all of us have been tested or know somebody who's been tested, and that experience is not very comfortable of having something being poked up your nose. There's been a lot of interest, as you all know, in developing better testing methods for COVID at various stages of the infection. And one of the topics of interest was to see if this test, the nasopharyngeal swab-based nucleic acid amplification test, could be replaced by an alternative method of sample collection that relied on saliva instead of the nasopharyngeal swab. And a meta-analysis based on this question was published by Guillaume Butler-Laporte and colleagues, who are also from the Department of Medicine. And they invited us to participate in this systematic review and meta-analysis together with them. So the nasopharyngeal swab-based NAAT is, considered the gold standard for detecting COVID-19 infection. It's been used over and over again during the last year, and I think it's really been the workhorse of the public health departments across the globe that have gathered information on the number of COVID cases daily and so on, helped us to manage the pandemic. But usage of this test requires trained personnel, and that can be a limiting factor, especially if you're working in settings where the necessary resources are not available. So a saliva sample-based NAAT seems like an attractive alternative, but its diagnostic performance was unclear, and it would have been reassuring to know whether it is comparable to the nasopharyngeal swab-based test. Individual studies that had been published in the literature at that point compared the saliva to the nasopharyngeal swab test and often assumed that the nasopharyngeal swab test was perfect, which is not the case. We know that this test can miss early cases, resulting in false negative results, and it can remain positive because that's the nature of the NAAT technology. It detects the genetic material, and which can remain even after the infection has subsided. So it can give a false positive result as well. So a fair comparison of a saliva versus nasopharyngeal swab should ideally take into account the fact that that nasopharyngeal swab-based test is not perfect. So the objectives of the study by Butler-Laporte were to estimate the diagnostic test accuracy of the saliva-based NAAT and to compare it with the diagnostic accuracy of the nasopharyngeal swab-based NAAT. They used good practices, the best practices they used. They followed the PRISMA guidelines. They registered their protocol with Prospero. And I will not get into the details of their systematic review. I'm going to focus instead on just the diagnostic meta-analysis portion of their study. And what was interesting for me was when they approached us to work with them, they were interested in applying the methods that we've worked on for many years to adjust for an imperfect reference test. It's something that most people are very reticent to use. So even when we have used it, often we'll say, okay, uh, we'll present the traditional meta-analysis in the main text, and we'll put this latent class analysis in the supplementary material for all those geeks who want to uh, you know check out what it can give as an alternative answer. But I was actually pleasantly surprised when uh, Guillaume and Todd Lee and I insisted that no, look, the correct analysis over here would be one that adjusts for the imperfect nature of the reference test. And so that became the primary analysis of this paper, though they do present in the supplementary text the traditional meta-analysis for comparison. So now I'm going to switch to the second part of our presentation. I'm going to talk about methods for diagnostic test accuracy meta-analysis. And frankly, this is a kind of humdrum topic, I think, in core especially. So many diagnostic test accuracy meta-analyses have come out of core during the last year, published in high-profile journals, BMJ and Annals of Internal Medicine, and so on. Nonetheless, I hope I can make it a little bit interesting to you. Like I said, for me, the uh, perhaps most interesting thing is what Ian is going to talk about. After years of working on these methods, we've really come to a point where we hope that we've developed something that will really make them much more accessible to a wider audience through this R Shiny app. So some terminology that we use in diagnostic test accuracy meta-analysis. This is terminology that's been developed by the Cochrane collaboration. The target condition is what the disease or the medical condition of interest that you want to detect. Index test is a test that is under evaluation. It could be a new test. The reference test is the most reliable method for detecting the target condition. And that's the test against which you want to compare the index test. Sensitivity and specificity, I presume most of you know what that is. It's so I won't leave that aside. And then prevalence is another statistic that one can measure. It's not to be confused with the population prevalence. It's often the referred to is the proportion positive on the reference test that they call the prevalence in these studies. But actually, that I will actually not be talking much about the prevalence, so we can ignore that as well for the moment. All right. So diagnostic test accuracy meta-analyses are nothing but meta-analysis, but used to summarize evidence across studies on both sensitivity and specificity of the index test. I mean, this has become the standard. Meta-analysis you might have already seen of randomized controlled trials where you're summarizing odds ratios or risk ratios across randomized controlled trials. It's the same concept. You want to summarize or calculate a weighted average across studies, except what distinguishes this type of meta-analysis, you're working with two parameters, sensitivity and specificity. And why do we work with sensitivity and specificity per se? Well, first of all, they measure test accuracy. They're more easy to interpret than other statistics, such as the diagnostic odds ratio, which is also a statistic that's used to evaluate diagnostic tests. So you might remember from your preparatory courses of epidemiology that a diagnostic odds ratio, which is illustrated here in this table. So you've got sensitivity along the columns and specificity values along the rows. And you can see that, and here within the cells of the table are diagnostic odds ratio values. So let's say a value of 76 for the diagnostic odds ratio can arise when the sensitivity is 95% and the specificity is 80%. But then you can also get a value of 76 when the sensitivity is 80% and the specificity is 95%. So if I tell you diagnostic odds ratio is 76, you don't know which of these two situations you're in. And that makes it more difficult to interpret, especially because the cost of a false positive and the cost of a false negative test could be very different. So you want to keep the errors in diagnosing an individual with the condition versus the error of falsely considering somebody without the condition as positive. You want to keep those two things separate because they might have separate costs, and that can be done in a more straightforward way when you're using the sensitivity and specificity. Also, another reason why we like to work with these statistics is they don't change in different settings because they don't depend on the prevalence. So predictive values, which are perhaps useful in clinical practice to make decisions, are less useful when you want to summarize accuracy because they would be functions of the prevalence, which would be expected to be different in the different studies in a meta-analysis. So we tend to work with the sensitivity and specificity. Now, if you want to work with these two statistics, a particular challenge that arises is that these two statistics may be correlated with each other, as is illustrated in this plot, which is, by the way, taken from one of our TB systematic reviews, which was, I'm just mentioning it because the first author is Mikash Mikoli, who's also at CORE. But what it shows you is that sensitivity and specificity could be correlated. And so we need a peculiar kind of meta-analysis model
Is Kaberi frozen? Is Nandini frozen?
Yeah, I think she's frozen.
Yeah, it sounds like it.
That includes correlations. Okay, just okay. Let me move to a cable internet connection that may be more reliable.
That's better, I think.
Okay, let me just move. Okay, okay, so I just want to say that one of the common biases that we recognize in these diagnostic test accuracy studies is the one that arises due to the absence of a perfect reference standard. We call it reference standard bias. And this table, by the way, you might recognize if you've done a diagnostic test accuracy meta-analysis or read one. It's based on the Quadus tool for evaluating the presence of bias in diagnostic test accuracy studies. And among the many biases that are recognized, this one, reference standard bias, is one that could potentially be corrected by statistical methods. So, something like blinding, for example, whether the interpretation of the index and reference test were blinded to each other, that's something you can't do anything about if you didn't take care of it in your study design. But something like reference standard bias could possibly be corrected if you're using statistical methods, but it's something we rarely do. So you'll take care of it in the Quadus tool. You'll say, okay, the reference test is not great, but then that's about it. We don't actually do anything about it. And the methods that we use, so these meta-analysis methods, I just want to say a couple of words about the models that we use. There's what's called the bivariate model and what is called the HSROC model. Both are really bivariate models because both of them handle this potential correlation between the sensitivity and specificity. And however, the Cochrane handbook which is something I encourage you all to look at. I think it nicely summarizes this, relevant literature in this area. It basically prefers the usage of the bivariate model, the so-called bivariate model, for instances where the same positivity threshold is used across studies. And they say HS-ROC is preferable for those situations where you expect the positivity threshold to vary across studies. And this, though frankly, those two models are algebraically equivalent when you don't have a covariate. And this Cochrane handbook is something that's available on the internet. Here's the link to it. I can share these slides. And it so happens Ian and I have contributed to the upcoming version of it. Chapter 11 in the upcoming version will have within it the programs that we've worked on over the years that use a Bayesian inference approach.
Nandini, I don't know how you want to handle that, but I saw a few questions pop up in the chat. Do you want to answer them at the end or as they come up?
Okay, thank you for interrupting. Let's see. Okay, I'm frozen. What is this? Teresa, wouldn't a common bias be how the test was administered? How the test was administered. Yeah, I'm sure that that's a bias, Teresa, and I'm sure it's something that's captured under this Quadus table. I think that indeed, perhaps I can ask that, address your question more specifically at the end. I'll ask you what you mean. And all right, so I think the rest of it is a conversation between Joanna and Teresa, but I'll pick up on that. We can pick up on that at the end of the conversation.
All right.
Okay, thank you for those questions, though. I think there's some good questions. All right, I just want to hurry on and say that, so I just have here some of the key references. This is a great article by Hans Reitzmer that describes the bivariate meta-analysis model. And here's a reference to another article we've written here that shows how you can extend it, apply Bayesian inference and a latent class meta-analysis structure. So just some quick words on the bivariate meta-analysis model. You assume that the studies are drawn from a common population, and the goal is to measure the mean of this population. So the mean sensitivity or mean specificity in this population. Like all meta-analysis models, there's an interest in between study variance while adjusting at the same time for within study variance. And we wish to take into account the correlation between sensitivity and specificity. I'm going to just jump across these slides in the interest of time. And applying a Bayesian analysis approach to this is not really more complex than the frequentist approach. You have to state the likelihood of the problem and provide prior probability distributions. If you have prior information, this would be a good way to incorporate it, though frankly, most of the analyses we have done have tended to use non-informative prior distributions. And so customary equations for a biostatistics talk, all I want to draw your attention to is that there are two levels in these models. There's the likelihood and the prior distribution. And if you want to extend the model to a latent class framework, then you're going to bring in some additional parameters. So if in red, you've got the additional parameters. So you, of course, have the sensitivity and specificity of the index test typically, but now you'll also be adding the sensitivity and specificity of the reference test as parameters in this extended model. You'll have the prevalence in each study as well, and the potential dependence, the conditional dependence which may arise because you want to correct for the possibility that both tests make the same error. So both saliva and nasopharyngeal swab tests may miss cases or may make false positive results. You want to adjust for that possibility, then you need to bring in these additional covariance terms. Okay, so I'm just going to go straight to the results. What you have here, I'm going to begin with the traditional meta-analysis. So if you ignore the fact that the nasopharyngeal swab tests could give results that are not accurate, then you would find that there's quite a lot of variability in the sensitivity estimates. The pooled sensitivity happens to be around 85%, but that is less than the 100% sensitivity that we're assuming for the nasopharyngeal swab test. The specificity, likewise, has quite a lot of variability. I mean, some studies report as specificity as low as 63% here, which would, of course, be unacceptably low. But on the average across studies, the pooled estimate is around 96%. This was what the bivariate meta-analysis plot would look like. So these meta-analyses are often presented in this sort of ROC framework. So you can see the trade-off between sensitivity and specificity. And there's a very large area here. Essentially, it tells you the same message that you saw on the previous slide, that there's a lot of uncertain variability in the sensitivity and specificity across studies. So this single point estimate really doesn't seem like a good representative value. You've got tiny dots, you don't see them very well, but they're scattered across a large area. Now, if I take into account the fact that the reference test may not be perfect, then you have the results at the top. And just for comparison, I still retained the traditional analysis at the bottom. So first of all, you can see all the specificity estimates now line up, and your pooled estimate of the specificity is around 99%. The pooled sensitivity decreases somewhat, the point estimate, from 85.4 to 83.2. And you might ask why? Because you think that, well, now I'm not treating the nasopharyngeal swab test as perfect. So that would imply that the sensitivity of the saliva test is going to go up. But in fact, what we're doing is adjusting for this conditional dependence. We're adjusting for the possibility that they both miss cases. They both make the same error. And that, in fact, brings the sensitivity of the pooled sensitivity down to 83.2% compared to the earlier estimate of 85.4%.
I think there is another question in the chat, Nandini.
Okay, I see that. It says, do you conduct tests of heterogeneity? And if so, should it be evaluated? If not, why is heterogeneity not evaluated? Okay, yes, I mean, you can indeed conduct, estimate the heterogeneity, though it's, the thing is, you expect heterogeneity in these tests. These are observational studies, and there may be very good reasons to expect heterogeneity. So, but yes, of course, you must try and gauge how much heterogeneity there is, because if there's a lot of heterogeneity, then your pooled estimate is not a good representative. Again, Amir, I'm going to answer your question in greater detail at the end. So we'll keep that in mind and come back to that. I'm going to just show you for comparison, this is what ultimately we want to look at. How does the saliva test compare to the nasopharyngeal swab test? And so the saliva test is at the top, the nasopharyngeal test here is at the bottom. And so the end result of this is that the two are very similar. One of them is at 83.2% and the other at 84.8% in terms of the pool sensitivity, and specificities as well are very comparable. So we concluded that they were in fact comparable, and the saliva test could replace the nasopharyngeal swab test in routine practice. And you can see that adjusting for this imperfect nature of the reference test also takes away that heterogeneity. So this addresses in part what Amir is asking about. But if you correct for this bias, then what seemed like a huge variability and specificity was in fact caused by ignoring the fact that the nasopharyngeal swab test can also be imperfect. And correcting for that means you see that the specificities are all lined up close to 100%, though there remains some variability across the studies in terms of the sensitivity. And I think that was related to the methods used for the sample collection and maybe the populations that were studied. So that heterogeneity should really be explored and explained as best as possible. So now I'm going to hand you over to Ian. I'll just say a word that this Shiny app, which was used in the analysis of this paper, by the way. So the analysis was done, though we're credited, and we did give a hand to the review and so on of the paper. Guillaume, the first author, was able to take this app and do the analysis and then come back to us with some queries. But it was very helpful that he was able to do a good part of it by himself, and I think he found it interesting himself. The app was developed by a student, McGill undergrad student called Mandy Yao, who is now a master's student at Simon Fraser University. So Ian, I'll stop sharing and it's yours.
Thank you, Nandini. Me too, I wanted to go to the beach next to the palm tree for the presentation, but sadly my Wi-Fi signal was not strong enough. So I'm here at my house. There's actually some plants behind. So I don't know if you can see them. So if we close our eyes, I guess it's almost like if I'm at the beach too. All right, so I guess all right, so what I'm going to do is I'm going to walk through the app directly from the browser and show with the data from the COVID-19 example how to perform these analyses. First, I'm just going to take the opportunity to say that this app, and Nandini, correct me if I'm wrong, but it can host a certain number of users at the same time, and I would think that if too many users, obviously, I guess we will be very, we will keep that very closely. But if we see, lots of people using this app, I think there are means to increase the number of users at the same time. But all that to say that there's a lot of things that can happen in the app that will just return you that error message saying you've been disconnected from the server, reload. And then when this happens, then we just need to click on the reload button. Oh, I guess I'll just refresh. Oh, okay, that was unexpected. Let's see. Is this something, I just want to make sure, Nandini, is this something related to the when you deployed the app, or is it on my side?
It's loading for me, Ian. It's for me. I'm able to load. So just refresh. Maybe you'll be able to get it. Yeah.
Okay. Let's see.
Maybe many people are trying to access it. I think this is precisely what
it could be what I just warned about.
Okay. So Ian is not able to access it. So I guess if maybe indeed you could all just wait till Ian demonstrates what to do.
So do we know, Nandini, what's the do you have statistics on that? What's the number of user
I
that can
think
actually?
I think right now it's set at some very low thing, like 2 people can use it at a time or
Oh,
something like
I
that.
see.
But we can easily increase that. Yeah. So try again, Ian, please.
Oh, okay. Do you see? I'm not sure which windows I'm actually sharing, which screen I'm actually sharing on my side. Let's see.
The one we see is the one that says "Cette page n'est pas disponible."
Oh, okay. So I guess I'll stop sharing and load this one.
Voila. Okay, good.
Okay, you do see it?
Yes.
Okay, great. So right. So this is there's actually 4 tabs in the app. So they are represented at the top of the web page. There's a home, manual, and either the bivariate or the latent class meta-analysis model. The home tab, I guess, well, you have a few references of, if you are interested in the methodology behind these models. But I guess what's most importantly is that we will try to keep the version updated through this information here. So we uploaded the latest version, which is dated from August 25 of this year. And so whatever new updates or edits or bug fix that we might actually do in the future, we hope to reflect that with some log file maybe that could keep track of what was added and so on. There's also, so in the next tab, there's also manual. I'm not going to go through this manual, as actually I'm going to be the living manual for this presentation. But basically, there are manuals for the bivariate Bayesian meta-analysis tab, as well as the latent class meta-analysis tab. I'm under the impression that they might be a bit outdated because we have made a few improvements and added a few options to the app since then. But I think that for now, they still give, a very general way of how the app works. And I will take the opportunity to also say that we have been working on a series of blog articles on these methods. And one of the blog is actually a blog that goes through this app in details, so in more detail. So that is something that will eventually, we will release that very soon. Okay, so I'm going to go, I'm going to look at this tab first. And I must say that there's a few variants between these two tabs. So the latent class meta-analysis has a few extra options. But I'll first start, going through the more traditional model, the one where we assume that the reference test is actually, a gold standard or a perfect reference test. And as we move to the latent class meta-analysis, I'll just highlight the options that were added under the LC A method. This app actually functions with the, so you need actually to provide a data set. So this is the only thing that you need to supply to the app. It's the data set. The data set, I will share it with you. So this is an example of the data set that the app expects you to upload. Basically, here I added a lot of stuff, a lot of information that are not needed. It was just information for me to keep track of, let's say, what is study 1? So what is this first row corresponding to? And what are TP, FPFN, TN? So these columns, header, what they mean. But basically, you could just remove that. The app doesn't need that. And in fact, this symbol here, always forget what's the English word for that. So the dièse, as we say in French. So this symbol is actually ignored by the app. So whatever you write next to that symbol can be just, it can be comments or or information that you want to keep track on your data. So what the app will take into account, though, is anything that is not preceded by this symbol. So basically, the app expects 4 columns. So you will need to provide 4 columns of data, just like it is organized here. And at the moment, it is really important that these headers be written exactly like this. So it's lowercase letter TP, FP, FNTN. The ordering of the column doesn't matter, but you need to provide these 4 columns in the data. If you don't, so if you, let's say, wrote TP with capital letters, it will for now produce an error. And well, basically what it will be, the message, I should say, that tells you that there's an error is that you're going to get disconnected from the server. The same message that we saw when I tried to connect to the app at the start of the session. So basically, this is what you need to provide to the app in order to let's see. Okay, this is it. So I only need to provide the data, like I said, to the app in order to run this model. So basically, I'll just go browse, and I was prepared already. So my data is there. And as soon as I click open, then there's a kind of progress bar that tells me, okay, your data was uploaded and you're ready to go. The settings, the setup of the app is such that you could just press submit from now on, and it would work without any issues. I'll start by going to the optional settings. So this is the place where you can set all these, MC settings, like the number of iterations that you want to throw away at the start, because these methods works iteratively, and there's kind of a adaptive step where you preferably want your model to converge before you want to include these iterations in your final statistics. So there's a certain number of those iterations that you want to throw away at the start, and then you can specify, once I have thrown away the first, here it's 5,000 iteration, how many iterations do I want to keep in order to calculate or to create my posterior distributions. So that is these 10,000 iterations that follows the burn-in step will then be used to create my statistics that we will get in the summary output. Since we're working with iterative process, it's usually good practice to have different starting points, and in order to assess that I'll, no matter where I start, everything converge to the same place. So this is done by setting what we call number of chains. So the default setting is to run 3 separate chains with different starting points, and hopefully they will all 3 converge to the same set of solution. And we also added in the last update an option to actually display how many decimal places after in your results. So that's for the optional step. I'm going to leave that as is. Then for reproducibility, and especially, I guess, for educative purpose, we also included a seed argument, which, if you uncheck the seed, then the app will kind of randomly select the initial values, and then the process of going through the iterative process and all that. And then if you get some results and you want to reproduce them, then it's up to you. It was random, so it would be difficult to reproduce the same exact result. When I say reproduce the same result, I mean to the exact decimal place. But if for educative purpose, then we could set a seed, ensuring that well, each time I run the app with the same seed value, then I will get the exact same results. So that can be helpful in trying to reproduce some examples that, like I said, if we want to do a workshop or things like that, I guess this is more for us that this option was added, but I guess there could be some values in that. And then there's a series, actually there's three more options, so three more boxes that you can check, which will allow you to, so if I click, let's say, this box here, so it will enable more options, where these are the different parameters that are being monitored by our model. And we have, so these model, I guess, Nandini kind of skip the section where these models were explained with formulas and all that.
Yes, I think that I would say our audience here, Ian, is familiar with these parameters. So
great.
Each of these, basically follows the pooled mean, sensitivity, and specificity across studies, the individual values across studies, and all of the parameters in the model. You can, and like Ian said, supposing you didn't check any of them, you just press submit, that would be just fine as well. It's really built to be sort of foolproof. Even the optional settings are set such that if you don't know what Bayesian statistics is all about, you can press submit and you'll get some, a first pass set of results that are, safe.
The only thing I will add, though, is that under the parameters shared across studies, there are two of them. So the last two, the positive predicted value and the negative predicted value, that needs to be checked because the user is asked to provide a guessed value of the prevalence, or in order to get these parameters being calculated. So if you would ignore that, then the model will just ignore these two statistics there.
Right.
And so that would be it for the Bayesian bivariate meta-analysis, and we would just need to press submit and we could get some result. I will, however, move next to the latent class meta-analysis. This is where I will just run the program and then we can look at the result quickly. So I will again load so it's the same data. I'm loading the same file, and I will just go through a few things that are, so basically what you see like parameters shared across studies, everything is pretty much the same. But what we have different in this tab are first the informative prior distribution. So the previous tab used some what we could say low informative prior distribution. The latent class and meta-analysis tab also use some low informative prior distribution. You could, however, for certain parameter, by clicking on this, specify some informative prior distribution. Basically, the app for now allows this for the sensitivity and specificity. So the sensitivity and specificity of the index test as well as the reference test. As it is, so if you leave this box unchecked, we're just going to assume that sensitivity and specificity of index and reference test so are likely to be from 0 to 1. So any value between 0 to 1 would be plausible. It's the place where you can actually change that. There's also the possibility to set initial values to some of the parameters in order to help with convergence. And then again, I will just leave that as it is. And then you can click on model conditional dependence to allow the model to just include in his model, include in the model the possibility that the index test and the reference test makes the same error, so they're correlated with each other. So I said I wanted to run this program, so I will just, however, increase this to 20,000, and I will set the seed to 1, 2, 3 as it is. So I just press submit, and one thing that lets you know that the app is actually running is, as you can, I don't know if you can see at the top, but there's kind of a black progressing bar that goes up. I mean that kind of moving, so you know that the app is actually, you know, it's not frozen, it's actually running in the background. So, and obviously the time it takes will depend on the iteration number, the number of iterations, sorry, the size of the data. So the more studies, the more time it takes. But usually these models are quite fast. And there you go. So we have, so the app has completed the process of you know, running in the background. And this is telling us, I mean, we know that as soon as there's data appearing in the data set, basically this tab just copy paste the data that we uploaded at this step. You know, one of the future improvement that I'd like to this tab displays maybe a forest plot of these you know, studies. So that's something that we have in our to-do list for the future. Then you have a series of tabs. So basically you have what we call the history plot. And density plot that are basically there for, you know, catching up any convergence issues that we, the model might, you know, go through. In this example, obviously, right now there's no way to zoom in through these plots. However, the, you know, I guess, fix around that is to select a certain parameters of interest. So let's say I'm going to look at the history of the mean sensitivity of index test. So I get a zoom of that plot. I could, let's say, add a second one, and then we have simultaneously the sensitivity and specificity of the index test, how they behaved, if there's any convergence issue or all that. There's also a you know, checkbox here to select those chains. So, you know, I said earlier that these were the starting points. We hopefully these starting points converge to the same solution. So we can actually select some of them. And in case, let's say, we find out that one is not converging yet, we could exclude it from the results and just keep the two others. Or, I mean, as many of the chains as we set in the options. So density, the same thing as history in terms of catching up if there's any convergence issue. And then we have the summary statistics. So right now, obviously, I have checked mean sensitivity and mean specificity there. I could uncheck in order to get the summary statistics of every parameters that were monitored by our app. And basically, you'll get, for instance, the 50% quantiles, which is actually the median, as well as the 2.5 and 97.5% quantiles, which are related to the 95% credible interval. So that's what Nandini was reporting in her slides for these parameters. And the summary ROC plot was created under this tab, where at first what we do see are only the summary points, which is given by that black dot, as well as the individual studies. I mean, the individual study estimates, so for sensitivity, specificity, given by these blue squares or blue rectangles. So as you can see, there's a very large study that dominates, and these other studies are smaller. So they are represented proportional to their sample size. So that's why some of them will be lower. So some of these rectangles are larger. And as you can see at the bottom, you have option to create these regions, so confidence and credible regions, as well as, credible regions and prediction region, as well as the summary ROC curve. So just by clicking on these options, you make these curves and regions appear. And I guess, so I guess it's up to 5, right? This presentation. So,
yes, that's right.
All right. So well, that would be pretty much it. Okay. I mean, I went quite fast, and probably that.
Thank you for accommodating your talk and the time I left you.
No problem, Nandini.
But indeed, thank you, Ian. And so we'd be happy to answer some questions. I'll attempt to answer a few questions that I saw earlier on. Teresa, you had a question about bias. Maybe you can explain what you meant.
So Nandini and Ian, thank you so much. This is a very exciting seminar. Thank you. I do understand the statistical novelty, and I love that you have an app and you can see your results, et cetera, and you can do good priors, bad priors, et cetera, and play around with that. My point is that before one pools data, that one has to be absolutely convinced that we're talking about the same methods that were used in obtaining the numbers for the different columns that you're talking about, the true positives, the false positives, et cetera. For example, in this number of studies that you presented, there were 13 studies, Ian and Nandini, in that data set?
Yes, there were 16.
There were 16. In a few of them, I noticed some had really high false positive and false negative numbers. So that for me would flag that study to say something's different about that study, than something makes that study different than the other studies. And so it comes down to my thinking that there are 2 types of heterogeneity. One is the statistical heterogeneity that one calculates in a meta-analysis, and the other one is the substantive heterogeneity related to the substantive disease or tests that one is using. And that needs to be understood first, so that when you're pooling results, you're pooling like with like. That's all I really wanted to say.
I think that's a very important, Teresa. And in fact, so I feel like what you're talking about is the heterogeneity that we can attribute to some known variable. For example, maybe the sample collection or the type of population. Maybe some studies were done in asymptomatic patients and others in symptomatic patients. I mean, these known sources of heterogeneity are what should be adjusted for, or we should create strata before we do any pooling. And what you're calling statistical heterogeneity, or the unexplained variability, is all what should remain. Anything that can be explained should first be taken out before we do any pooling. And I think that we don't do that. I mean, especially if you see even meta-analyses published by the Cochrane collaboration, often you do systematic review and you first pool everything, and then you do an exploration of heterogeneity. And I would argue that we should go in the opposite direction. Maybe if you know ahead of time that certain things can cause heterogeneity, yeah. So I agree with you, and I think that relates somewhat to Amir's question as well. How do we measure heterogeneity? I think that I would be interested to measure heterogeneity after, like you're saying, having removed all these known sources of heterogeneity, and then you can say, okay, even after removed everything I know about, is there, whatever 30% or say 90%, or how much of variability remains unexplained? And then that I-square statistic is interesting.
I just jump in. Just
Yes.
it's a good conversation. I think it just boils down to there's statistics and then there's epidemiology. So you're talking about, Teresa, is the epi side and looking at the different biases. There's the spectrum bias of the diseases. There's different types of tests, and some are more user dependent. And so we should be doing a critical appraisal of all of those things. The reality is often there are a limited number of studies to pool, and sometimes people just throw them together, or others would argue this is the right and wrong subset. So I guess what you're showing, Nandini, is once you've presumably gone through all of those proper steps, then you proceed with the analysis, which should be the way we do things. But I guess the Shiny Act is not going to fix that.
Yes, exactly. And indeed, I glossed over all of that when I said I'm going to focus on the diagnostic test accuracy meta-analysis. I'm hoping that Guillaume and Todd Lee and Emily McDonald did a good job of identifying a group of comparable studies, and we focused on the meta-analysis. But yes, I mean, I think that these are very relevant questions to us. There's not much point in just throwing together, studies that are not even comparable to start with.
Which is why Lawrence Joseph used to always say, don't use that I-square, look at the studies and make your assessment. Is there clinical heterogeneity or not? Don't rely on a number to tell you. Yeah.
Right. Yes. And any other questions? Ioana, do you have any questions or comments? Okay. So it's 5:03. And if there are no other burning questions, then I'd just like to thank all of you for being present and for patiently listening to us present these methods through the technical glitches. And we'd be more than happy to do a workshop at CORE to share in greater detail both the theory and the practice of these methods. So thank you very much.